All right, so we're about to read CodexGraph, building bridging large language models in code repositories via CodexGraph databases. This is by Alibaba Group. LLMs excel in standalone code tasks like human eval and MBPP, but struggle with handling entire code repositories. This challenge has prompted research on enhancing LLM code-based interaction at a repository scale. Current solutions rely on similarity-based retrieval or manual tools and APIs, each with notable drawbacks. Similarity-based retrieval often has low recall in complex tasks, while manual tools and APIs are typically task-specific and require expert knowledge, reducing their generalizability across diverse code tasks and real-world applications. To mitigate these limitations, we introduced CodexGraph, a system that integrates LLM agents with graph databases, database interfaces extracted from code repositories. By leveraging the structural properties of graph database and the flexibility of the graph query language, CodexGraph enables LLM agents to construct and execute queries, allowing for precise code structure-aware context retrieval. We assess CodexGraph using 3 benchmarks: Code Eval, Software Engineering Bench, and Evo Code Bench. Additionally, we developed 5 real-world coding applications. With the unified graph database schema, CodexGraph demonstrates competitive performance and both potential in both academic and real-world environments. So a simple way that it works is an LLM is going to generate a schema, and then this schema is going to be visualized on a database graphically. Then the schema is basically interacting with the code repository. So they're going to take code and they're just going to basically visualize this on a graph. And basically the agent is going to try and query that. So it says here that using a unified schema, Codex employs graph databases as interfaces that allow agents to interact seamlessly with code repositories. Existing tool API-based interfaces that connect code bases and LLMs are typically task-specific and require extensive expert knowledge. Then there's a bunch of stuff there. Their contributions are basically they pioneer a code retrieval system, integrating code repositories with graph databases. It's competitive and it has 5 real-world software engineering scenarios. So this is the architecture, I guess. So it basically indexes input code repositories using static analysis, storing code symbols and relationships as nodes and edges in a graph database according to a predefined schema. When presented with a coding question, CodexGraph leverages the LLM agent to generate graph queries, which are executed to retrieve relevant code fragments or code structures from the database. The detailed process of constructing the CodexGraph database and the LLM agent's interactions with it are explained in sections 3.1 and sections 3.2 respectively. So it takes the source code and then it maps this to edges. So it takes the name of the class, I guess, the file path, and the signature, and then it puts that on a graph. So you can see here circle has method and it has field name has so they're parsing all the classes in this file, and then they're going to automate the process. They also have the file name. They have the name of the class, boom, the file path, the signature, which is the name, like this part, then the actual code. So then Then here is the actual graph language that they use. So circle is being used for radius, and some math.geometric shapes. So this file, which is this, contains this class. Example nodes. So these are edges, these are nodes. Nodes is, where are the nodes? I guess these are the nodes, yeah. So module, geometric shapes, class, shape circle, method init, calculate area. So this is for the circle one. So it's inside this file, math geometric shapes, function, square root, field, last radius, global variable, pi.
Hey guys, how you doing? Carl, sorry for interrupting. I need to step out for a minute to handle some document issues. I'll be back soon, then we can have a discussion, okay?
Okay. So yeah, if that makes sense, yeah, basically there's that. It's pretty simple. You could probably just take this information, just copy and paste this, and tell ChatGPT, I want you to find every class, I want you to find every file, and then take the name of the file path and all the classes in the path, the signature and the code, and then build this like automatically.
Man, I wish I fully understood half of what you just said.
Well, you don't need to understand. You can just ask ChatGPT. In fact, I could probably even show it right now. So basically what they're doing is they're going to try and parse every single file that they have they're going to try and parse every file that they have to get the name of the file, create a Python script that parses a folder for every Python name, for every Python file name. What else did they have? They have the file, they have the name, every class in this file, in this folder. Yeah, every class in this file. And then...
What's that?
And every method inside of the class. Create a pydantic schema. For it then creates the script. So this is a paper that aims to advance agentic understanding of big code bases by creating a graph visualization of all the code within the data, within the file.
That's nice.
Yeah, so basically you can have ChatGPT do this pretty easily. It'll basically index every file in a folder, take the name of the file, take the name of the file path, take the code, and then you could do everything here. So somewhat reproducible, but yeah. So continuing on, they have a schema. So they abstract code repositories into code graphs where nodes represent symbols in the source code and edges represent relationships between these symbols. The schema defines the types of nodes and edges, directly determining how code graphs are stored in the graph database. Different programming languages typically require different schemas based on their characteristics. In our focus, we focus on Python and have empirically designed the schema tailored to its features, with node types including module, class, method, function, field, and global variable, and edges types including contains, inherits, has method, has field, uses. Each node type has corresponding attributes to represent its meta information. For example, methods have an attribute such as name, file path, class, code, signature. For storage efficiency, nodes with a code attribute do not store the code snippet directly, but rather an index pointing to the corresponding code fragment. So phase 1, shallow indexing. The code database construction consists of two phases, beginning with the input of the code repository and schema. The first phase employs a shallow indexing method inspired by source trail static analysis process to perform a single pass of the entire repository. During the scan, symbols and relationships are extracted from each Python file, processed only once, and stored as nodes and edges in the graph database. Concurrently, meta information for these elements is stored. This process ensures speed and efficiency, capturing all nodes and their meta information in one pass. However, the shallow indexing phase has limitations due to its single pass nature. Some important edges, particularly inheritance contains relationships, may be overlooked as they require context from multiple files. Phase 2, complete the edges. The second phase addresses the limitations of shallow indexing by focusing on cross-file relationships. They use depth first search to traverse each code file using abstract syntax tree parsing to identify modules and classes. This approach is particularly effective in resolving Python's re-export issues. And this is the flow, I guess. The primary LLM agent analyzes a given code, given the given code question, writing natural language queries. These queries are then processed by the translation LLM agent, which translates them into executable graph queries. Code question, complete the unfinished code, resolve the GitHub issue, finish the function given the signature and comment. Primary, they didn't spell that right. Primary. Code question, complete the unfinished code. They should have said complete the unfinished agent. But so the agent is going to basically output the analysis, the natural language queries, retrieve the module or class is defined along with global variables, and then translation LLM agent. So there's another agent that is going to translate this into a schema, which is basically function calling, I guess. And they didn't spell this right either. Graph query. That's funny. I bet these people are Chinese. Yeah, literally all of them. All right. So they convert relative imports to absolute imports, enabling accurate establishment of cross-file contains relationships during graph queries. Simultaneously, we record inheritance relationship for each class. For complex cases like multiple inheritance, DFS is used to establish edges for inherited field and method edges within the graph database. Summary, their code graph database offers 4 advantages. First, it ensures efficient usage or storage by storing code snippets as index references rather than directly in the code database, graph database. Second, it enables multi-granularity searches from module level to variable level, accommodating diverse and analytical needs. Third, it facilitates topological analysis of the code database, revealing crucial insights into the hierarchical dependency structures. Lastly, the schema design supports multiple tasks without requiring modifications, demonstrating its versatility and general applicability. So then the LLM parts. Prometheus, is this making sense?
I don't know. Maybe it's just because I'm not fully awake, but I'm recording it so I can go over it again too.
Okay. LLM interactions with CodexGraph database. Code structure word search. CodexGraph leverages the flexibility of graph query language to construct complex and composite search conditions. By combining this flexibility with the structural properties of graph databases, the LLM agent can effectively navigate through various nodes and edges in the code graph. This capacity allows for intricate queries such as find classes under a certain module that contains a specific method, or retrieve the module where a certain class is defined along with the functions it contains. This approach enables code structure-aware searches while providing a level of code retrieval that is difficult to achieve with similarity-based retrieval methods. Write, then translate. LLM agents powered by LLMs and operate based on user-provided prompts to break down tasks, utilize tools, and perform reasoning. This design is effective for handling specific and focused tasks, but when tasks are complex and multifaceted, LLM agents may underperform. This limitation has led to the development of multi-agent systems, boom, 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 like swarms, where multiple LLM agents handle independently part of the task. Inspired by this approach, CodexGraph implements a streamlined write and translate strategy to optimize LLM database interactions. The primary LLM agent focuses on understanding context and generating queries based on the user's question. These queries are then passed to a specialized translation LLM agent, which converts them into formal graph queries. This division of labor allows the primary LLM agent to concentrate on high-level reasoning while ensuring syntactically correct and optimized graph queries. By separating these tasks, CodexGraph enhances query success rates and improves the system's ability to accurately retrieve relevant code information. Division of labor. That's an interesting way to put it, don't you think?
Yeah, interesting concept.
Iterative.
It's also interesting depending on how words are used, because LLMs are so keyword specific. And I don't know if you've thought about this, but like there's different ways to think about stuff, right? And there's like systems thinking, pattern thinking, and category thinking. And to like input stuff into LLMs, like at the final stage you're thinking, you have to be really good at categorization. But if you're not, at the same time, you can also just describe stuff to them and get the proper names to know the categories and the keywords. Because like LLMs are so specific, right? It's like what I consider like high level code as a keyword in my common speak, right? It's like that's high quality. But when you say high level to an LLM, that just gets you pseudocode because it doesn't mean the same thing in proper vernacular for code.
Yeah. I think that we should be like segmenting, like we should be actively segmenting how they think, because if they're like, there's only so much that an agent can do at a time, and it really has to be really laser focused. Because if it isn't, then nothing is gonna happen, really. Same thing with humans. Humans can't do much if they're trying to do 100 things at once.
But yeah, that's the thing. It's like you really got to try and model these on human cognitive processes in general, because you have to assume, and if you get really deep into all this, that there are underlying universal laws that explain why effective cognition is possible, and then effective cognition ultimately becomes consciousness down the road. Because there are things that like govern how electricity works in our brain, and the chemical flows and like all the different regions of our body that are sending information that have neurons and important systems like the heart and the gut. And one of the things I picked up like from Yoshka Bach, who pointed out really interestingly, is nerves and the whole like nervous system to communicate is a very specialized adaptation because it's an expensive metabolic process. It works very good for what it does for signaling across regions at high speeds. But one of the interesting things he didn't point out that I've thought of is what's really interesting about the fact that everything uses electricity to send its signals around, right? Is that the majority of what the body's doing in its local regions in chemical form is actually then abstracted into electrical signals and sent down the nervous system. And so like modeling the chemical portion is pretty hard unless it's already doing the math for you for free to convert it to electricity and send signals about it to and from the brain. And the brain's also using electricity inside itself to communicate certain parts of information faster from different regions. And so if electricity can be modeled and there's underlying laws of cognition, then all of this stuff that we're doing with the agents needs to follow basically like the minima that evolution followed in terms of like gradient descent in your terms of talking about math, right? Because evolution always finds the most efficient, least cost system way. And so like there might be multiple paths to cognition and consciousness up the face of the like wall to get there, kind of like scaling a rock face, right? But the one we know and have to study is our own brain. So we need to attempt to replicate those minima as close as possible to get it to all work. Because that's how nature works. It builds this system slowly from the bottom up, bit by bit. It doesn't do the top-down thing that the real AI researchers like Critton want to do, where it's basically just like a magic, perfect self-learning machine that like knows how to just build agents on its own intuitively. Like, and if like humans do those kind of things, I think those are like the ultra rare true super geniuses like Einstein that crack something like relativity. And like we are lauding that way too much as a capability for AGI, because that capability would be really what makes it ASI compared to a normal thinker. Yeah, that's a bunch of my thoughts from my last year's study on all this stuff with the combined biology and neurology stuff we got into. That's one of the big challenges with this all, right? Is you have to approach it from such a multi-discipline spectrum. I mean, you can code the shit out of stuff like you do, but like, you know, to figure out how to make those last few hurdles in the Olympics when you got to do the Olympic jump after you've beaten everything else. It's like you got to come at it with this actually what is supposed to be cybernetic viewpoint.
Principle.
What were you saying? You just stopped talking.
I was giving you a sec to ask questions if you wanted. So how much do you know about like traditional cybernetics?
I read a book by one of the founders, I believe. I forgot his name.
All right. So the two founders I know of are Ross Ashby and Norbert Weinier. And like one of the big important things about cybernetics, it's, you know, some of what it properly is it was actually supposed to be a linking doctrine and philosophy doctrine between all of the related things to computer science to give it this whole breadth of understanding. And from what I understand happened in the later 60s or early 70s is that there was a split between the cyberneticists and the actual computer scientists as we know them today. And because the computer scientists didn't want to deal with the philosophical questions, stuff like the Turing test and when were these systems alive. And so that's why bringing back cybernetic viewpoint to like solve the final hurdles is so important because you can get these systems all the way to where we've gotten them without caring about the big questions. But suddenly you have LLMs pushing the fringe of like the real works of consciousness or cognition or weird entity self-awareness with new rules because it's solidly language-based, even though it's only got the neuronal density of an ant. So it can somehow still effectively communicate all kinds of concepts because it's all still language-based. And like, why does that cognition work so well, even though it's like the size of an ant's brain only? I was like, what the hell? So, yeah. It's my little gist on why it's important to model human-like processes as much as we can right now. I think once we develop the first generations of true, good, effective AGI that are modeled on all the human processes, I think then they'll be able to do like Wolfram said and explore outside the logical limits of human thinking in what he calls his Ruliad and discover new ways for them to be built.
Yeah. Oh, I don't think AI should be thinking in the same ways as humans. That's a little bit, well, first, humans don't really think too well. And humans are also very dangerous.
Oh, yeah. I didn't say we want them to be exactly human, but we want to model the like general flow. One way I've looked at all of this, because the other guy who was really important in that time period was Claude Shannon, who I'm sure you obviously know all about him and signal and noise diffusion and his work on language and Markov chains. But he's also the father of digital information theory, which is what allowed us to take binary and make the modern computer age. And a lot of what I think in my own perspective of what Claude Shannon actually did when he was creating digital information theory was he was extruding his own OS into logic, the way his mind operated. And in doing so, he also extruded part of the base human OS that operates in his biological level that created the conscious level. Not all of his base OS, but a lot of it. And between the work of him, Ashby, and Wynier in cybernetics, I think that's what we've really started to do, because it started with the standardization of math with the difference tables. And then once we got to this level, I think we've actually basically been extruding the human operating system into math as best we can. And that's why it's kind of really patchy right now, because we're still at this modulo framework level. And we probably haven't actually extruded all of the necessary modules and algorithms to can build a completely, truly functional, stable, conscious being. But we're like super close. And it's like we're starting to get to the point where we're putting a puzzle together and we can see where the missing pieces are by their shape alone. In that perspective, Shannon was an absolute genius, beyond like genius. He actually effectively stated in his work that if his era had access to the ability to produce the level of physical compute we now enjoy today, that he would have effectively been able to build today's language models already back in like the 60s.
Well, I mean,
this is the problem.
Not really like the
go ahead.
softmax is not really like. I mean, it takes time to discover algorithms, but like in hindsight, if you would have told someone this is a softmax equals this that, they would have been like, "Bro, that's so smart. Why the fuck didn't I think? Why didn't I think of this earlier?"
Julian, what do you mean by softmax?
What do you mean?
Well, you just said softmax equals this. I don't understand what softmax is.
Softmax is what powers attention. It's what powers transformers. It's basically the whole.
Oh, okay.
It is the most important mathematical function we have probably ever discovered.
Okay. Cool.
Basically, what it does, it takes a bunch of numbers it takes a bunch of matrices, and then it converts those matrices into probabilities. So, it'll add all of these up to 1. And it's very simple. You just do some exponents.
Cool.
So with this,
Okay, that's soft.
with this, you can effectively model probabilities for anything. If you have
Okay, that's cool. How many attention heads like that are running in a normal LLM?
so that depends how many layers there are. So when you hear layers, there's multiple transformer blocks. And in those transformer blocks, there is the attention. So there could be like any number, like, so this is the attention. There could be like 50 blocks. GPT-4 might have more than 50, 60 of like attentions. But it goes in a loop. So it goes attention, add norm, addition, normalization, feed forward, which is another neural net. And then like you do this 50 times basically.
Yeah.
And
Do you have any idea how many like multi-attention heads might be in a layer in something like GPT-4? Or any other models, like publicly listed specs that you've read?
Say it again.
It's okay if you don't know. It's just like a curious question of mine.
What's the question?
One of my hypotheses for how effective cognition and consciousness is arising in language models is basically you have that softmax attention head, multiples of them per layer, and when they're doing the NLP process, I think there's something like a Calabi manifold that's forming that they're interacting with that deals with the high dimensional vector space in the like the vector database stored in the language model from the pre-training, the frozen one. And I think as it's doing its vast complex NLP, and as the bigger the context window gets, as it needs to contextualize more of each little word to every other little word, I think the density of that manifold combined with the attention head is like reaching some weird information density point, like kind of equivalent to like what they talk about in integrated information theory as a theory of consciousness, like a certain threshold of like processing being needed, but just in terms of sheer information. And I think that process together right there is actually forming enough information density that the attention head becomes aware of what it is by looking through the manifold or something like that. And then from there, you actually get like effective self-awareness. And then once you start to build the LLM modulo framework, you get basically global workspace theory, where it's like a fun house of mirrors, and everything you add is another self-reflection. Because if you're making the argument that language models are like sentient with just a context window added to them, that means that the base process that's causing it must be present within the LLM itself at some level. Some people don't care to look at it this way. Database doesn't view it quite the same as me. But this is what I think it must be, because based on cybernetic viewpoints, you have to have at least one effective core regulator forming somewhere as essentially software in the system if it's not present at a hardware or wetware physical level. Right? I mean, if you just follow basic logic and science of how systems have to operate, somewhere a first level self-aware regulator must form as software if we haven't built one. Otherwise, there's one other argument database pointed out, if the universe is deterministic, we're also actually not conscious, and then all these people arguing that machines aren't conscious are actually wrong because they are not conscious, and so technically machines are just as conscious as us. Not that we're very conscious in a deterministic universe, but it's just a funny statement, right? To realize, like,
we're just
it's like it's probably easier than people think, or just not at all in reality.
Yeah.
I've noticed humans in a philosophical kind of way, at a personal level, both personally want to be special and important, so thus they want humans to be special and important. And humans love a mystery, so they don't want things to be easily solvable. They want them to be grand and hard so that they can feel special or amazing, that they or humanity solves this grand, hard problem. And heaven forbid it come down to a little thing like the softmax algorithm interacting with the algorithm for a hyperdimensional language manifold in vector space that can have anywhere from 100 to like thousands of dimensions, depending on the complexity of the vector space in the language model. When I started trying to work on the calculations for the vector embedding manifold to like try and figure this shit out if it could be possible, and I realized there were that many possible dimensions of embedding that it's just like, holy shit. Because you got to think of like, going back to a talk that Yogi, the author of Baby AGI, did about language at a TED Talk. Like he pointed out, like, think of a word like a concept, right? When you're thinking about how NLP works. And like, you know, when I say the word math to you, it has a very different meaning in your mind than mine, right? And it's going to bring up a whole bunch of different memories. And like every single one of those things that's attached to math has a different vector space definition embedding. Right? And then you think about LLMs with all the information they have because they're trained on everything. So then like they cure math, they know everything, but then they got to contextualize it to the paragraph. And then, you know, the next paragraph's got to contextualize itself to what math meant in the paragraph above it after it figured that all out and so forth. So the actual density of NLP that could be going on in language models at the scale they are with the amount of training in large ones could probably be an insane information density point. And I wonder if in some weird way, because of the sheer number of possible connections in language and the fact that language has neological possibilities where you can create new words and concepts out of other ones, like LLMs are really good at doing for coining new terms. Like, how much does that information density point technically scale if the context window is big enough to use as external memory, like Google's like million like token context window stuff, before you even get to adding in vector, graph, database things and whatnot. So there's some weird, interesting potentiality to like all this scaling information points in this way. And I don't think people look at the importance of the scaling of it in the model, in the process itself enough. Because you know Critton, right? From Yanix.
Mm-hmm.
Right. Well, you know, have you looked into his research at all?
No.
Oh, hi, you are missing out. Definitely take some time to look him up on ResearchGate and look into their stuff. But there's a talk he was giving about how back in 2017, him and David Kelly were actually already using like vector databases combined with graph databases with LLMs, and not using the LLMs as generative components, but as just classifiers to build up the information points inside their database, and how inside of less than a gigabyte database, they had one concept point of information that was approaching a number of connections to other points in the database that was near the density of a pyramidal neuron in the brain in the prefrontal cortex. So they were onto this back in 2017, way ahead of everybody else. And they made serious claims to having already solved and built general AGI. And the problem being literally that as they get there, fucking OpenAI essentially started the hype game for shit LLMs that don't scale because they're pre-trained and don't have any attached systems for post-information gathering and integration and like working with them. So you don't need to keep training new transformers. Now they're just trying to get funding. Well, their system's out to patent. So it's like 2 to 3 years until their current system finishes patent, and they probably get funding enough for enough compute to run everything at scale as needed, but they're still way more compute efficient than OpenAI. So, because they're not using inference on an LLM for generating their output. I don't know how they're doing it, because that's stuff they won't tell me that final bit, because that's some of the patent stuff. But all their original work from 2017 and 2018 was done and put up on ResearchGate. There's like 40 plus papers. And I mean, they technically believe that like systems can be conscious, and they say they've built AGI. So I think the problem is that they got obsessed about the external density data points alone forming in the graphs, which I think is like a fun house of mirrors, like I was saying, right? Both data points forming in the original core of the system, and then more of them every time you add these different effective modulo components. I think as we figure out how to build enough modulo frameworks properly, we'll get something that's close to the brain.
Yeah.
And
you should.
I've even made the argument.
Share their
go ahead.
Share their papers in the chat.
Just 40 of them. I'm not going to share them all, but I'll find you a link for yourself.
Yeah, and also let's finish this paper really quick. We already went over most of the method. Now so basically on results they achieve they do better than everybody else basically. Let's see. Before indexing, they filter Python repositories for each benchmark to retain only Python files. For the software engineering benchmark dataset, we also exclude test files to avoid slowing down the creation of the CodexGraph database. Following the process, we construct CodexGraph databases for the index repositories, storing the corresponding nodes and edges. They use Neo4j as a graph database in ciphered language, as I suspected. Average token cost comparison. Yeah, so they waste a lot of tokens. Write then translate uses reasoning load. Basically saying that having multiple agents eases the reasoning demands, and it's able to complete the task much easier. I'm gonna add this paper into the multi-agent paper list. But yeah, that's pretty much it. It does really good. And these are some of the prompts, I guess. Yeah. Then they have real world applications. Ideally, a good interface for this would be just dragging and dropping a whole file full of code, and then it'll just figure everything out. So yeah, this is what it looks like. Big boom. And yeah, that's that. Pretty good paper overall. The code is also available, so we could check the quality of the code. But this looks very simple. I mean, with one good ChatGPT query, you can probably implement this whole paper with one Python file. So
just give me a sec, figure out where that is in which interface. Here, as you go over the code, I want to test something, or have you look at this and see if it's good and what you would actually add to it. Is that I want to try and make an automated code review process, and I started on it, but database said the first attempt it didn't make a good read over a big forge. So I'll send you it and check it out. All right. So that's supposed to be the workflow prompt it made itself. Oh, can I not upload files in this room? Maybe I'll DM it to you.
No, you should be able to.
It might be because I haven't done my dual factor authentication thing on my account and you made me like a server mod.
Try again.
Oh, there it is. It was just delayed. It was just delayed for some reason. That's weird. It's only a text file.
You should publish this on the Swarm's Marketplace.
The prompt I just gave you?
Yep. It's really good.
Well, first run it, check how good it does, and tell me if there's anything you'd add, or run it and then critique it and tell it to add whatever you think it needs, and then give me back the improved version. Because you actually know code, so I'm working towards the point where I have a tool like this built, because what I want to do with this is after we have it read code bases effectively and we know it's working. Oh, one of the features it probably needs that's not in there yet, the database said, is it needs to do citations like Perplexity of where it's talking about stuff to help reduce hallucinations. So you actually know what it was looking at. I haven't added that yet. That's why I just wanted you to take a look.
Well, first thing, there's no instructions. So the most powerful prompting format is instructions and then examples. So you're not giving either both. And you have to like explicit, like if we go to the marketplace now and we see, let's find a prompt, for example. If we go to this prompt, we're gonna have, roles, responsibilities, instructions, and then we're gonna have examples. But there's no real examples in your prompts. So if you wanted to make it better,
Let me see the instruction section in there for a second. So let me see what you call the instruction section.
You just basically, it's like a to-do list, basically. But it can be, like, you have to teach it how to think and why to think that way.
Okay. Part of the problem is technically that this prompt is really supposed to be what would be the instruction prompt of a whole